So, hello everyone, welcome back to machine learning lecture. So today we'll be starting K-Nearest Neighbor. It's one of the most simplest algorithms that you will see in machine learning. And you might see a little bit of similarity in this algorithm when compared to K-means algorithm. Though K-means is an unsupervised learning, this K-Nearest Neighbor is a supervised learning algorithm. So this is supervised learning algo. But you might find some similarities with K-means as well. Learning algo. Okay, so let's dive in. So what we'll be doing today? So we'll be first of all looking at what is the algorithm for running a K-nearest neighbor classifier. And then we'll be talking about the decision boundary of KNN, also called or particularly one nearest neighbor, which is also called just nearest neighbor classifier. Okay, so if somebody asks you what is nearest neighbor classifier, it means that it's just one nearest neighbor. We'll get to what is this K nearest neighbor, one nearest neighbor. And then we'll talk about the bias and variance paradox in K nearest neighbor classifier. Okay, so let me start. So I'll just start with the algorithm at first go because there is literally no derivation to it. It's just the classifier and there is a particular algorithm to it. So what is the algorithm? So if suppose you receive a QI as a data point for which you need prediction. So in supervised learning setup, we had seen that we always want to do predictions on test data. So we always want to do prediction on test data. So here I'm calling it a query point or just one data point that you received and I'm calling it a query point. So QI is basically a query point. So what you will do is you will first standardize all of your features and have them centered such that it has zero mean and variance one. And we had seen this in K-means as well, why we do it. Because uh, if they are in different measures, if the unit of different features are different, what can happen is that a feature which is on higher unit, which has values like 1000, 2000, and suppose there is a feature one, this is a feature two, and this is a feature one which has values like 0 0.1, 0.2, right? And I convinced you that this feature basically will contribute more to decision making rather than uh, they being equal, right? So if I standardize this, they will become equal. So the problem of this features being on different unit can be solved using the standardization. So for the same reason, we'll standardize the data so that they have zero mean and variance one. Okay. And now what you'll do is based on some distance matrix. So in distance, so when we were studying K-means, we had talked about distance matrix, right? So studied during K-means. So if you have not watched that lecture, you can go and watch it. So there are different distance matrix based on different type of data that you have. So we'll use one of those distance matrix to find the K nearest neighbors. So how do you define the K nearest neighbors? So they basically are some K data points. So I'll just uh, go here. This is the K. So these are K training data points. Training data points at lowest or minimum distance. So they're at minimum distance from the query point. So there are some training data points which will be at some minimum distance from the query point that you're talking about. And you will just, so what you'll do is you'll take the query point, you'll compute the distance of that particular query point with every point that you have in training. And then you will find the points, you'll just pick K points, which are at the lowest distance from this query point. And then what you do is you take a max vote. What is a max vote? So suppose that you choose 3 neighbors. Okay, and one is saying class positive, one is saying another positive, and third neighbor is saying negative. Okay, so you will do a max vote. So you'll do max vote of this. So max vote is basically positive, right? So majority is saying positive. So we will classify this particular example as positive. Okay, so max vote is nothing but taking the say of majority, whatever is the majority saying, you will take just that and you will assign that particular label to the query point. Fine. And if there are, suppose now what can happen is, suppose you had chosen 4 neighbors, which we usually don't do. We usually take odd number of neighbors. But suppose somebody is giving you 4 neighbor classifier and you have one neighbor saying positive, another neighbor saying positive, one neighbor saying negative, and another saying negative, right? So here I have a clash. I don't know whether I should classify it as a positive and negative. Here, either they will give you like, how do you want to break ties, or you can randomly just break ties and assign it to the query point QI. Okay, so here you will say random of positive. So randomly you will flip a coin and you'll assign either positive or negative to that query point. Fine. So this is this simple. This is a very simple algorithm. There is no rocket science in this, no derivation in this. This is this simple, but this simple algorithm is also very beneficial on a lot of kind of data. For example, ECG data, I have used this K-Nearest classifier and or K-Nearest neighbor classifier, or say if you have to do the iris data classification, there also it can create good prediction values for you with good accuracy. Fine. So any doubt till here? Any doubt? Clear? Very simple algorithm. We'll solve some questions on this. So this will become more clear. Okay. So this is the first question that I have. So in this particular lecture, we'll be solving a lot of questions. Not lot, 8 to 9 questions we'll be solving. So it'll give you like complete idea of this particular algorithm. Fine. So this is question 1. It's saying that consider a set of 5 training examples given as xi, yi, ci. Okay, so these are 5 training examples over here. These are training examples. Just a sec. So these are training examples. So you have 5 training examples. Where xi and yi are 2 feature attributes or 2 attributes. Okay, so these 2 values are basically features. These are features or attributes, as you can call it. And they are all in positive integers. Fine. Then you have CI is the binary class label. So there are 2 labels here. So there are 2 classes. There is a positive class. There is a negative class. Okay. So +1 or -1, there are 2 classes. It's saying classify a test example, which is at coordinate 3, 6. So the example that we have here is at 3, 6. And we have to classify this using the KNN, where we have to use K is equals to 3. Okay. And we have to use, so they have also specified what distance metric we have to use. So they're using Manhattan distance. So Manhattan distance is nothing but for every feature, you'll compute the absolute difference and you'll just add them up. Fine. So this is absolute difference between the first feature. This is the absolute difference between the second feature, and you're just adding that up. That is Manhattan distance. So now they're saying that you should use Manhattan distance and you should use 3 nearest neighbors to classify this data point. Let's see how to do this. Okay. So this is your query point 3, 6. So first of all, we'll compute the Manhattan distance. So here I'll compute the Manhattan distance. Okay, so the point I have is 1, 1. So I'll do 1 minus 3 and take an absolute value of that, and 1 minus 6. I'll take the absolute value of that. So this is what? This is 2 plus 5, right? So this is 2 plus 5. This is equals to 7, right? Similarly, we'll compute the distance for this. So this is 1 minus 3 plus 1 minus 7 minus 6, right? So this is 2 plus 1, which is equals to 3. Similarly, we'll compute the Manhattan distance for this particular point. So this is 3 minus 3, which is 0, plus 3 minus 6, which is equals to 3. So this is 3, right? And then you have 5 minus 3 plus 4 minus 6 is equals to 2 plus 2, which is equals to 4. And then you have 2 minus 3 plus 5 minus 6, which is equals to 1 plus 1, right? 2. Fine. Now we will find nearest neighbors. So which are the nearest neighbors? We have to find three nearest neighbors. So we'll say 3 nearest neighbors. Okay, so which one are the 3 nearest neighbors? So this particular point I can see is the closest. Then this particular point is also the closest, and this particular point is the closest, right? So now we have to do max vote. So this is, let me call them DP1, which is data point 1. This is DP2. This is DP3. This is DP4. And this is data point 5, right? So data point 2, 3, and 5 are my nearest neighbors, right? So the nearest neighbors are DP1, DP2, DP3, and DP5. So I'll take a max vote of this. So I have to do max vote of, so DP2 is positive 1, DP3 is saying positive 1, and DP5 is saying negative 1, right? So I will just take a max vote, which is positive 1, right? So we will classify this as a positive example, or example belonging to the positive class. Clear? Simple? So this is very simple, right? Okay, fine. Okay, so let's see the solution. So this is the solution that we have. And I've taken this example from some good university. So you can check that this handout as well. Fine. Okay. Now let's do second question. So second question is asking you to do it for k is equals to 4. And the data point that you want to classify is 2, 2. Okay. So let's do this quickly. So we'll compute distance over here. So we'll do 1 minus 2 plus 1 minus 2, which is equals to 2. 1 minus 2 plus 1 minus 7, which is equals to 1 plus 6, 7. Then you have, sorry, I made a mistake over here. So this is 2 minus 7. Okay, let me just go back and do it correctly. 1 minus 2 and 7 minus 2, which is equals to 1 plus 5, 6. This is 3 minus 2 plus 3 minus 2. So I can reverse the order here, right? It doesn't matter because we are anyways taking absolute difference. So we can reverse the order, or we can subtract them in any order. So this is 1 plus 1, which is 2. Then you have 5 minus 2 plus 5 minus 4, which is equals to 3 plus 1, which is 4. And then you have 5 minus, sorry, 2 minus 2 plus 5 minus 2, right? So this is 0 plus 3.
Fourth one should be minus 2, no? 4 minus 2.
Sorry. Here, yeah. I made it a mistake. Sorry. This is 2, right? So this is 2 minus, this is 2. This is 3 plus 2, 5, right? 5 minus 2. And this is 4 minus 2, 2. Okay. This is 5. So this is 3 plus 2, which is 5, right? So what are the 4 nearest neighbors that you have? Nearest neighbors. Okay. So the nearest neighbors are, so let me call them DP1. And I'm calling them DP1, DP2 just for your reference. When you're doing it in the exam, you don't have to do this elaborated calculation and this elaborated thing. You can do it very quickly, right? So the nearest distances are this, 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 and this, right? So this is the farthest away point. So here we have DP1, DP2, DP3, DP4, and DP5. right? So I will take a max vote here, max vote of these. So this is -1. This I'm not counting. This one is +1. This is -1. And this is, what did I do? -1, +1, -1, -1. Okay. Okay, so now you have negative. Fine. So this is the predicted classes -1. Fine. Okay. Now let's do. Okay, so this is the example. Now let's do the other question, which is question 3. Now I'm saying that you have to classify this point 1, 1 using K-nearest classifier with K is equals to 5. Okay. So can you do this and let me know what is the answer? Okay. How come you are doing this so quickly? Okay. So do we need to compute distances here? Yeah. So do we need to compute distances over here? No, right? Because there are only 5 data points, right? And so even if you compute distances, only these 5 will be your nearest neighbors. So we don't have to compute the distances. So what we'll do is we'll just take the max vote of this data, right? And when we take the max vote of this data, so max vote of all the data, max vote on training data, whatever training data you have, sufficient, or is the answer, right? So be careful in the exam. So if they give you these data points and they give you the K to be the exact number of data points that they have given you in training, you don't even have to compute the distances. Just look at the max vote of all the classes and or of all the data points, and you will have your answer, right? So max vote of this is, so I'll just write it, max vote of -1 +1 +1 -1 is equals to -1, right? So the answer is mine or predicted class. Fine, very simple, right? No rocket science in this. Okay, fine. So there are few more things about K-Nearest Neighbor classifier, which are just properties. So this is the memory-based classifier. What is the meaning of memory-based classifier? That all your data points are just your, you store all the data points, all the training points are sitting in your memory. All training points are in memory, right? So what it does is it just stores every data point that it has in its memory, and it uses just that and no other parameter, right? Obviously, K is one thing, but you don't learn it as a part of training process. So there is no training involved. So there is no training involved here. No training involved. So all your data points are is basically your model. Fine. So there is no, so this is a memory-based classifier, and there is no requirement of fitting any model. So whenever you train a neural network model or say linear regression model or logistic classification model or logistic regression model, so there you're fitting your model to the data, right? You're learning some parameters, W, B, etc., right? So here you don't have to fit any model. You will just take all the training points that you have, you load them in your memory, and you'll start computing the distances. Fine. And given a query, what you'll do is you will find all the distances from all the points that you have, and you'll pick the K-nearest neighbors from that, and you'll just use a max vote. So So for every data point, you always have to calculate distances from from all the data points. Obviously, there can be some optimizations done, but in an unoptimized implementation of K-nearest neighbor, you will actually calculate distances to every other data point, and then you will choose your the K-nearest neighbors. Does that answer your doubt, Rohan? So Rohan has a doubt that do we have to find the distances of every new query point? Yes, we have to find distances corresponding to every query point. Otherwise, how will you classify it? So first of
Yes,
all,
ma'am.
right? Clear, right?
मैम सो यहाँ पे जो बोल रहे हैं ना कि all training points are in memory, memory based classifier mainly. तो
Yes.
मेमोरी बेस्ड क्लासीफायर मतलब क्या, वो डिस्टेंस के बारे में बोल रहे हैं या फिर जो ट्रेनिंग पॉइंट है वो अपने
The
मेमोरी
training
बेस्ड?
point, the exact data point, you just store it in your memory. And what you do is every time you compute your distances or every time you receive a query point, you go back to your memory, you recall, okay, these are all my data points. You will compute distance corresponding to every other data point and then find the minimum distances. So all it's saying, it's a memory based classifier, as in it just learns every data point that it has. So every data point is in the memory, or it has learned every data point. That's what a memory based classifier is. Okay. Now, given any query, suppose that you get a query for some x naught, we will find the k training points which are nearest to this. Okay, so we will find k training points. Training points means the data points that were present in your training data set. You will find the k most closest training points, and then you will use it to classify using max vote. Fine. Then ties are broken at random. So it can happen that you have ties. And mostly it will happen in a setting where you have even number of k, or k is an even number, and hence we try to avoid an even number as k. And if you happen to choose k to be an even number, you can break the ties randomly. Fine. Or if they are giving you a question that you have to use some even number as the k nearest classifier's k, then they will specify you how to break the ties. Fine. Now, this is also a lazy classifier. What is the meaning of lazy classifier is that the prediction calculation, whatever you're doing, is delayed till the query point is received. Okay, so you don't do anything till you don't receive any query point. You just remember all the data points that you had in your training data, and you don't do anything. Once you receive a query point, then only you start your calculations. So hence, this is also called a lazy classifier. Fine. Clear? Now I want to add over here one more thing, which I didn't add to slides, but as we are doing. So K-nearest neighbor classifier. I'm saying it K-nearest neighbor classifier. This can also be used for regression task. Regressor. Okay. So what you will do is you will pick closest K neighbors. Okay. And then you will do some mean or mod or some statistical value will calculate, like median over predictions of, sorry, not predictions, over true values of k nearest neighbor. So this is not nearest neighbors, right? So suppose that you have, I'll just make up an example. So suppose you have 1, 1 and 3, 2, 2 and 4, and you have a 3, 3 data point, which is say 5. Okay. And I'm saying, so I'm just making this up. So suppose your data point is 5, 5. And they're saying use k is equals to 2. Fine. So this is no longer a classify. This is no longer a classification problem. You can still say that this is a classification problem. I want to model it as a regression problem. So I will say this is a regression variable or a regression feature. Fine. So I will not take it as a class 3, 4, 5, I will say it as a value which is like 3, 4, 5. So how will I do it? I will find the nearest neighbors. So what will be the nearest neighbors to 5, 5? There'll be 2, 2 and 3, 3. Right? And I'll specify that you have to take the mean of the value. Mean of the value. Okay, so I'm asking what's the prediction for 5, 5 point. So for 5 point, what you'll do is you'll take the mean of this, which is 4. You'll take 4 plus 5 by 2, which is 9 by 2, which is 4.5. Yes, so we are not talking about whether it's going to work or not, but you can use regression. You can use K-Nearest Neighbour as a regressor or not. Here, probably it's a very bad example because here for 5, 5, it's giving me value 4.5, which is over here. Though you can see that it should probably should have a value like 7, right? So I'm not saying it's a good regressor. All I'm saying is you have a method of doing regression using K-Nearest Neighbour as well. Okay. So it's not every algorithm will work for every kind of data, right? For some places, you will have a classifier or a regressor working very nicely. And at the same data, some other classifier might really mess up. So we are not arguing like what kind of data this will work on, what kind of data this will not work on. I'm just telling you that there is a method of using it as a regression for a regression problem as well. How it's going to perform in that regression problem, that we'll see with the evaluation. And how do we do the evaluation of these kind of classifiers or regressions? I think you've already seen it. For classifiers, you will compute scores like accuracy, you will do AUC, ROC curve, you will compute precision recall. For regression, you will do mean square error, mean absolute error, and kind of those kind of things. Fine. But there is a way to do the regression using K-Nearest Neighbour as well. Okay. Fine. Now let's do one more question. So you have to tell me whether this is true and false. So as the value of K used in a KNN, which is K-Nearest classifier, is incrementally increased from 1 to n, where n is your total number of training data points, and the classification accuracy of training set will always increase. So here I'm saying classification accuracy of training set. Okay, what is the meaning of training set? A classification accuracy of the training set. So you have remembered your training set already, right? Now what you'll do is you'll classify the, when I'm saying training set accuracy, basically how good it's classifying the training data points. Fine. So let's do this if you're not able to see this. Okay, so let's do it and we'll know it how it works. So let's take the case of 1NN. Okay, so if I take 1NN, what will be the accuracy? So if I take 1NN, so let me call this the data points A, B, C, D, E. C, D, and E. These are A, B, C, D, E points, right? So if I take 1NN, one nearest neighbor, and I'm saying that I'm calculating the accuracy of the training set only. So it means that I want to calculate the accuracy of A, B, C, and D, and E, right? So what is the true label of these? This is positive, this is positive, this is negative, this is positive, and this is positive, right? So if I'm going to take 1NN, what will be the predicted label? So it will find the nearest neighbor of this training data point. And in this particular case, because we are computing we are classifying only the training points, with 1NN, every data point will be the nearest neighbor of itself. Correct? Every data point is nearest neighbor of itself. Nearest neighbor of itself. Is this clear? Why is this? Because I'm computing the accuracy on the training data set, right? So the predicted value will be exactly the same. So this will be the predicted value. So accuracy is 100%. Fine. Now let's take two nearest classifiers, right? Or two nearest neighbors. Let me again rename them as A, B, C, D, and E. So this is my point A, B, C, D, and E. Okay. Now let's talk about the data point C. Okay, and this will only give us an idea. So for C, we'll try to find the nearest data point, two nearest data point. So two nearest neighbors will be C, and you can take any of these neighbors because it's equidistance from all of them, correct? So we'll have, say, C or A, and then we'll break ties randomly, correct? Yes, fine. So in this case, there is a chance that this can get classified as positive, can get as positive, though this is a negative point. Yes, right? So what happened to the accuracy? So accuracy can decrease or it will decrease, and we'll see that it will decrease in the next example. Can I say anything about the A point? Again, the same thing will happen, right? So accuracy, not 100%, not always 100%, right? So it's not completely 100%. Same will happen with A also. So the nearest points will be C and say B, right? Then it's a 50-50 chance that it will be classified as a positive or a negative, right? So the accuracy is not 100%, not always. Let's do more concrete case where we have three nearest neighbors. So there is no tie, right? So we have A, B, C, D, and E. Okay. So let me talk about C point now. So C will look out for three nearest neighbors. So they'll be, say, A, B, and C. Correct? So this is, so it will be first of all closest to itself. So C is by default its neighbor, the closest neighbor. Then it can pick any of these neighbors. So it can pick A or B, it can pick A or D, it can pick A and E, and any neighbor, right? So if this happens, any of the neighbors, right? Any two positive neighbors, and C itself will be the neighbors, right? No matter what I do, when I take a max vote on this, what will be the predicted value? Prediction is going to be positive, right? So it will always have max vote of positive, positive, and negative, because C will always have two other neighbors which are positive as its neighbor, and we are talking about the three nearest neighbor classifier. So the prediction will be max vote of positive, positive, and negative, which is equals to positive, right? So for sure, C will be classified incorrectly, right? So accuracy for sure will decrease, not 100%, right? And what was the question asking us? That if we increase K from 1 to N, the classification accuracy for training example or the training sets will always increase, right? So this is true or false? So this is false now, right? Okay, so this is false, proved by examples. Fine. Okay, now let's do question 5. Okay, and this is a PYQ which was asked in GATE DA 24. This was a 2-mark NAT question. Also, I had solved a similar question on the YouTube channel in around January. So people who watched it got benefit from this because they were able to do it very easily. Fine. So let me read out the question for you. So given two-dimensional data set consisting of 5 data points from two classes, circles and squares. So there are two classes, circles and squares. So this is class 1 and this is class 2. Fine. So there are two classes. Assume that the Euclidean distance is used to measure the distance between 2 points. So they have given you the Euclidean distance as a distance metric. They will always specify the distance metric that you need to use. Now they are asking you that minimum odd value of K. So you have to find the minimum odd value of k in the k-nearest neighbor algorithm so that the diamond shaped data point is assigned the label square. So where is the diamond shaped data point? So this is the data point. Okay, so this is your query point. Right? So query point should be assigned the label square. Okay, and they're asking you for the minimum odd value of k. Now you have to find the minimum odd value of k. So they're asking you k is equals to what so that diamond point gets a label of square. Okay, can we do this? So first of all, focus on odd value of k, right? So k is equals to can be 1, 3, and 5. Correct? So k is equals to 1. So what is the nearest point to this diamond point? 1, 1. Right? This is on a diagonal distance. So this is definitely greater than this particular distance, right? So this distance, because it's on a diagonal, and this is also on a diagonal. So these two are farther away from this 1, 1 point, right? So nearest neighbor is 1, 1. So prediction value will be circle. Okay, so definitely k is equals to 1 is not our answer. Let's do for k is equals to 3. Okay, so for k is equals to 3, what will happen? So for k is equals to 3, we'll have obviously 1, 1 is our nearest neighbor. And what will be the nearest neighbor here? So these 2 points, right? So this circle 1, 2 is the nearest, and then 3, 2. You can do it visually. You don't even have to compute distances over here, right? So here, now you have 3 points. So these 2 are circles. So this is a circle. This is a circle, and this is a square, right? So your prediction value will come out to be circle again, right? Now you can stop here and just say k is equals to 5, but let's do it for the sake of completion. So you have 1, 1, 1, 2, 3, 2, 3, 3, 1, 2, 1, 1, 3, 2, 3, 3, and 2, 3, right? So first of all, I don't even have to compute anything. You can just take a max vote on this. So I will just take the max vote on this, and obviously now I know this will be classified appropriately. So this is a circle. 1, 2 is a circle again. 3, 2 is a square. Correct? This is also a square. And this is also a square. Correct? So the prediction value will be square. Right? So hence k is equals to 5 is our answer. Right? So first of all, there are ways to do it very fast. So just you don't even have to write all of this down. You can just quickly see that, oh, this point is there. So in k is equals to 1, this is the nearest data point. This is the nearest data point in k is equals to 1. Then in k is equals to 2, k is equals to 3. This is these two are nearest. So this is the nearest point and this is the nearest point. K is equals to 2 anyways, you don't have to do. So these are the 3 nearest points. You don't even have to calculate the distances, right? And in k is equals to 5, obviously all the data points are there, 5 data points. So no need of computing distances, just take a max vote on this. Right? And max vote on all of these data points will be square. So hence the answer for this particular question is 5. Okay, so 2 marks for free. Like 2 seconds, 3 seconds. Okay, let me assume you'll take 5 seconds, 5 to 10 seconds to read this question. And next 10 seconds, you should be able to solve this without any calculations. Fine? Fine? Okay. So, good. Now, any doubts still here? Otherwise, we'll start talking about the decision boundary of KNN. No doubt? Okay. So what is the decision boundary of KNN? And this is where I was saying that you will find similarities with K-means. So the boundary lines are formed by the intersection of perpendicular bisectors of pair of points And you will use points which are in opposite classes to create your boundary, and it'll become clear. I'll show you an example so that you know how to create the decision boundary. And if there are if there are boundaries which are um classifying the points into the same class, you will just remove them because they are redundant. Okay, so I've made 3 statements. I'll go over them one by one. Okay, so suppose that you have this data set. Okay, and so there is some classifier at work. Probably it's one NN classifier at work. So you are just looking at one nearest neighbor of some classifier or of some data point, and then you are basically classifying. Okay, so how will you construct the decision boundary? Decision boundary for 1NN is very easy to create, but for say 2NN or 3NN, it becomes difficult and more complex. But if you understand 1NN, you can kind of visualize how the decision boundary for k greater than 1 looks like. Okay, so I'm talking about 1NN over here. So this is 1NN. Okay, so um, so first of all, we'll look at data points which are in different classes. You will find the data points which are in different classes. So this is the nearest point of this particular point, which is in a different class. Okay. Similarly, these 2 points are nearest to each other and have a different class. Similarly, this point over here is nearest to this data point in a different class, and this over here, right? So they will be the deciding ones. Deciding ones because suppose I create, okay, so let me first create the decision boundary. So what I'm saying is I'll join these two and I'll create a perpendicular bisector of this. Okay, so I'll create a perpendicular bisector of this like this. Okay, then I will create perpendicular bisector of this particular line. So it will be something like this. Might not be very appropriate, but and then I will create a perpendicular bisector of this. So this will be something like this. Right, and similarly I'll create a perpendicular bisector of this, right? So why are we creating perpendicular bisectors? So when you're taking Euclidean distance in consideration, so assume that I'm using Euclidean distance in consideration. So whatever point is here, right, on in bit, so this, suppose I take a point which is at equal distance from this green point and this yellow point, right? Then this point will be in a conflict that should I go to the green class and should I go to the yellow class, and you have to break ties. But what about this point? Suppose I have taken a point which is here, right? And let's not consider any other data point here. So if this point is there, we know that this data point is closest to yellow data point, right? Because its distance from green data point is much farther, right? So this particular data point will be classified as yellow. If you take any other data point over in this region, right? Any other data point, any point you will take over here, they all will be classified as yellow, right? So, and suppose I take any point over here. So this will be classified as green because compared to this yellow point, they are closer to this green point. So any point you take over here, they will be classified as green, right? So the center of these 2 points, this center is basically your decision boundary, that it's telling you that points to the left are in one class, points to the right are in the right class, the other class, right? So you do it for every point, every pair of points. Fine. Suppose I do it for this particular point. So if I do it for this particular point, what will happen is, even though so any point which is here or any point which is here, it will always be classified as yellow, right? Hence, this decision boundary is redundant. Because any point which is here, it will also closest to yellow. Any point which is here, which is closest to yellow only. So the prediction for this particular, any point which is lying in this region is going to be yellow only. Hence, we don't have to create the decision boundary here because decision boundaries are created only for separate classes. Here, it's classifying it in the same class. Hence, we can just remove this. So we can remove this. So we'll remove this. So we'll do it for every data point, but we'll remove the decision boundaries which are redundant. For example, this particular decision boundary will be redundant. right? So this is also redundant because to the left also you of this particular decision boundary, it will be something like this, right? To the left also you have the decision bound, you have the class as yellow. To the right also you have the class as yellow, right? So it doesn't matter. Fine. So I had stated these many points. So I had said that boundaries are formed by intersection of perpendicular bisectors at every pair of points. Using pair of closest points in different classes will give you a good approximation of your decision boundary, and you will remove the boundaries that are classifying in the same class. Okay, so that's what we have done. So this is what you will construct. You will create boundaries like this, and this is what it is, right? This is how you will construct the boundary, and this is your decision boundary. After you have constructed these white lines, you will remove these perpendicular bisectors, and this is your decision boundary. Okay, so you can see that this is one class. So this is class green. This is your class pink. And this is your class yellow. Fine? Easy? Okay, fine. Yeah, Rohan, what's the doubt?
मैम तो अगर इन ट्रेनिंग डेटा पॉइंट है और अपना सपोज स्मॉल एम नंबर ऑफ क्लासेस है और हमसे पूछा जा रहा है कि 1 NN में कितना डिसीजन बाउंड्रीज होगा, तो वी कैन से MC2 में नहीं होगा, राइट?
नहीं, so decision boundary is just one.
ओके ओके
So this combined thing is a decision boundary. So how you're separating these three classes is the decision boundary. There are
ओके।
no multiple decision boundaries.
तो मैं हर एक लाइन को सोच रहा था कि वो एक
No,
डिसीजन
no, no,
बाउंड्री
no. This is the decision boundary. This is how you create the decision boundary. This complete thing, this white thingy, is your decision boundary.
ओके मैम, या गॉट इट।
Right? Decision boundary basically tells you how you are separating classes. So it's not that this individual is a decision boundary. No. So this full construction is the decision boundary. Okay. Fine. Okay. Now you should be able to solve this question. So this is question 6. So figure 1, which is below, there are two plots, illustrates decision boundary for two nearest neighbor classifiers. Okay, so they are telling you that they are nearest neighbor classifiers. Determine which one of the boundaries belong to one nearest neighbor classifier and which one belongs to three nearest neighbor classifier. Okay, so can you tell me which is one nearest neighbor and which is three nearest neighbor? Let's do this. Okay. So let's do this one. Okay. So if you do this one, this will become easy, right? So this is one nearest, suppose this is one nearest neighbor. Okay. Or let me just remove this particular thing. Probably not a very good idea to do it like this. I'll erase this decision boundary and then we'll create one ourselves. Okay, so let me see what will happen if we create decision boundary for 1NN. Okay, so the point that I will focus on is in this vicinity, because here I'm seeing a lot of contradiction, right? Here, if I create those perpendicular bisectors, they'll be redundant because all of them are negative points. So I'll try to construct decision boundaries around here with 1NN. Okay, so suppose I have, so this is one. So this is one point of contradiction, or a point which is between these two will have a classification like very differently, right? So there'll be a perpendicular bisector and something like this will be constructed. Similarly, with this negative point, something like this will give me the decision bound. Like this will tell me that, okay, points in this region will be classified as negative. Points in this region in this particular region will be classified as positive, but in this particular region will be negative, right? Similarly, when I do this, something like this will tell me that points to the left of this will be classified as positive, points to the right of this will be classified as negative. Similarly, this will give me a perpendicular bisector over here. And then I have with this also I'll do, or probably I don't need to do it over here. With this I'll do. So this is like this, right? And with here, they are both basically classified into the same points, but actually the decision boundary of this will be like this, perpendicular. Let me just edit this out. Yeah, so this will be like this. So this is a line like this. So you'll have something like this, right? So in 1NN, this particular data point, which is a negative data point, it's creating a closed boundary around itself, right? Even this is the full boundary that we have, right? So this should tell me if a point which is sitting outside, so this is negative point, is basically a outlier or a traitor or a black sheep or anything you want to call it, right? So this is sitting in between all of these positive points. So if I'm going to use one nearest neighbor, points which are in this particular region will be classified as negative. Right? And this gives me hint of how the one nearest neighbor classification will do. So I can confidently tell that this particular figure that I'm seeing over here is associated with a one nearest neighbor boundary. And this is probably a 3 nearest neighbor boundary. So here also you can see, suppose this point is over here. Okay. So what are the nearest neighbors to it? This positive, and this negative, right? I take a max vote, it will be classified as positive. Probably a neighbor over here, right? So this is nearest neighbor over here is positive, then positive, and one negative. So points which will lie in this particular. So another way of doing it is you take points over here, like here, and you will take points over here. And you will just ensure that if I take a point over here and I take 3NN, right? So these are 3 nearest classifiers. So this is being classified as positive, which is correct because this is the decision boundary and left to this are positive points. Similarly, if you take any point over here, you will take 3 neighbors. You will see that, okay, this is being classified correctly in the negative set. Hence, you will be able to ascertain yourself, or you will be very certain that this is a 3 nearest neighbor boundary. But if they are given you like a 1NN, 3NN, just know that 1NN has very local structures like this. This is a very local boundary that you have. Okay, so it will give you a hint on what is a 1NN boundary and a 3NN boundary. Another thing to notice here is that as you increase the number of your nearest neighbors, right, your decision boundaries tend to become smoother, right? You can see that this boundary is quite smooth. Over here, this is not so smooth. You can see the segments, line segments like this. Right, so this is not a very smooth boundary over here. Probably this is also not the correct way of doing it. It's something like this only, but they are much smoother than your one and nearest neighbor. Fine. Yes.
Why you said they should be like a segment of lines or line segment joining?
Because see, you will construct like this. This will actually be like a boundary. So how do you construct boundaries? You create using perpendicular bisectors only. So these are line segments only. So you'll
But for
take
three,
vicinity. You take vicinity of 3 points. Obviously, this is difficult to construct, but I'll show you an example where it'll become where I've constructed the boundaries using the data points.
okay, yeah. Sure.
Okay, so there's one question that can we say that when we increase the number of k, the effect of outlier decreases? Yes. So as you increase the number of your k, your model tends to become more robust. Robust means that it's less sensitive to the outliers, because now it's taking more points into consideration for making your decision. If you're just going to consider just one point, then your complete decision is dependent on the nearest data point. It might be an outlier also. So yes, with as we increase the number of K, we actually tend to build more robust classifiers. Right? Okay.
But मैम, as we also हम लोग जितना K को increase करते रहेंगे, the chances will be also higher that we may include some outliers.
No, so what is the meaning of having outliers? How much you are sensitive to outliers? So suppose that you have this class. Okay. Now, if I'm going to use one nearest neighbor, what do you think will be the prediction for this point?
Will be minus.
So if I'm going to use three nearest neighbors. So in one NN, this will be predicted as negative, right? In 2NN, you will use more neighbors to predict. Let's talk about 3NN, right? So then it will be positive. What do you think this point should be, positive or negative?
Positive.
Positive, right? So here, because you're taking just one point into consideration, you are the points which are in closer vicinity of this. So here over here, whatever points are there will be classified as positive. Sorry, negative, which is wrong prediction. So it's more sensitive to outliers.
But when you increase the K more and more, तो हम लोग ऐसे बोल सकते हैं कि to
The
certain
prediction
level.
will be wrong. No. So what I understand is that you are saying that the prediction can become wrong.
Yeah.
Right?
So it is getting affected to the outliers again.
It's not getting affected by the outliers, right? It's getting affected by the total data points. Not just one example is affecting the decision.
Okay,
Here
here
just
outlier is this. Okay, yeah.
yes.
Right. Yeah. Got you.
Yeah. So where as we increase, okay, the classifier becomes more robust to outliers. Fine. Now I'm going to talk about any other doubts. Any doubts? No. Clear. You know what is an outlier, right? I'm assuming you guys know what is an outlier. I just use that terminology. Okay. Outliers are basically points which are not following the data pattern. Over here, if you don't know, so here this negative point is not following the data pattern, because we can clearly see that positive classes are over here and negative data points are over here. But this particular data point being negative is sitting over here, right? So it's an outlier because it's not following the data pattern or data distribution. Okay. So now let me talk about bias variance paradox in K-means classifier. Okay. So first of all, answer me this. So this is a little bit of your revision from your bias variance trade-off class. So model with high dash pays very little attention to the training data and oversimplifies the model. And model with high dash pays a lot of attention to the training data and does not generalize on the data which it has not seen before. Okay. And the options that you have to fill in are bias and variance. So what is the bias and variance? So tell me what is, let me call this option 1. Let me call this option 2. So what will be the answer in option 1 and option 2? Okay, fine. So the correct answer is actually bias. High bias models, they pay very less attention to the training data and they oversimplify the model. Okay. And high variance pays a lot of attention to the training data, and hence you will see a lot of fluctuations in your prediction values. So have you not seen this in the class? I was assuming that you've gone through this bias variance trade-off. If not, let me go over it a little bit. Okay. I don't know if you guys have seen this before, but this is how we see it in this is how we see the bias variance trade-off. Okay. So let me talk about high bias first. Okay. So high bias and low variance, right? So here, this is your true class. Okay. So this is your true predictions. Right. So these are your true predictions. And here, what happens is that your prediction values are way off, right? It's not at all learning what is there in the data. Whatever training data it had, it probably didn't learn anything. It has low variance because you can see that the prediction values, these yellow ones are the prediction values. You can see they are not that much scattered when I compare it to this particular dartboard, right? Here you can see there is a lot of variance in the predictions, right? So this is variance in the predictions is high. Variance in prediction is high, right? And here you can see that this is low variance. Similarly, here you can see that the values are scattered, but now it's paying a lot of attention, or it's predicting very close to your original data values, right? Whatever you had in your training data, it's predicting closer to that. Obviously, there is a lot of scatter. So the variance is high, but the bias is low, right? And we usually aim for a model which has low bias and low variance. Fine. So this is to the point, the variance is less, and also it has low bias, so it's paying attention to the data whatever you have. Okay, so this is what the question was. That model with high bias pays very little attention to the training data and oversimplifies the model, right? High bias models tend to be very simple. For example, um suppose this, suppose my data is like this. Okay, suppose my data is like this, and I say that this is my prediction value. This is my say this is my regressor or predictor. Let me say this is my regressor. This is the regressor I have trained, and this is my true values. This is my true values. So what I've done is I have oversimplified my model. I'm saying that this polynomial, maybe some x degree polynomial, I'm trying to predict it using a linear classifier or linear regressor, right? So I have oversimplified my model over here. Right, and this is, so what will have, so here you will have very high bias, correct? Will have a very high bias because this is a very oversimplification of the uh, model that you actually had. You should have fitted a model like this. You probably should have fitted a model like this, but you fitted a very simple model to it, and hence the model is very simple, and so its prediction values will be way off from your true values. Fine. We prefer high variance toward overfitting. No, so if you have high variance, you will have a lot of overfitting. High variance means that even with a slight change in your prediction value, your value will be changing a lot. You should not have a model like this. Obviously, it's very difficult to achieve a low bias, low variance model because of bias variance trade-off. But you try to minimize or balance out both. You don't aim for a high variance model. Have you studied that in class, that you look for a high variance model? No, right? I'm assuming you guys have not studied that. You try to aim for a low bias, low variance model because that's, I will show you this example again, okay? Here. So this is a better model. If you aim for a high variance model, what will happen is that for a slight change in your data value or say your features, you will have very different prediction values, and you don't aim for that. Suppose, so I'll tell you a problem with having a high variance model. Let me go over here. So this will happen with high variance model. Okay, so if you have high variance model, suppose I'm saying years of experience and say salary. Okay, I'm having a very simple model over here. So say years of experience, 3, 4, 5, 6. Okay, so salary is say 30 lakhs. This is 40 lakhs. This is 50 lakhs and this is 60 lakhs. It's a linear model. Suppose I fit a very high variance model, which, or let me just say 45, 50 and say 65. Okay. And you always like when I talk about this much salary. So let's say I say 3.1. Okay. So what will high variance model do is a high variance model will predict the variance in the prediction value will be too much. So it'll be like probably it'll predict 36 lakhs. Right. So your so you so in so there is though there is a slight change in of your years of experience, you're getting 6 lakhs more, right? Just 1 month probably, not 1 month, 2 months approximately. You have more of experience, you're getting 6 lakhs more, right? And compare it with this guy who has 4 years of experience and is earning 45 lakhs. Probably not a very good example. I should keep it 40 only. So what will happen is with slight changes in your X, your Y will change a lot, and we don't aim for that. Fine. So over here also you can see that with slight changes in X, your values are like they are very scattered. If you do this, your prediction values are not good. Fine. So we aim for low variance, low bias, but it's not always possible because of bias variance trade-off. Hence, we try to settle, like come at a place where we have both kind of things balanced. Fine. Okay. Now let's do this question. Okay. So if I increase K in K-nearest models, what will happen? It will increase the bias and increase the variance, increase bias and decrease the variance, decrease bias, increase the variance, or decrease bias and decrease the variance. Think about it. So if I increase K in K-nearest models, K-nearest neighbor models, what will happen to my bias and variance? Okay, no answers. Okay, I'll give you a hint. What happens when K is equals to N, total number of training points? So think about the extremes. When you have K is equals to 1 and K is equals to N, what will happen? If K is equals to N, what will happen? For every data point that you have, what will be the prediction value? Okay. What will be the... Okay, so when K is equals to 1, we know that this is overfitting. So the variance is very high, right? Now let's talk about K is equals to N. So here we have reached a conclusion where K is equals to 1. Then we know that variance is very high. Variance is high, right? And it's kind of overfitting. Right? And when K is equals to N, what will happen? What will be the prediction value for any data point that I give if K is equals to N? So it'll give me same prediction value, right? So can I say that variance decreases? So there is no variance in the prediction, right? What about bias? So I've oversimplified my model, right? There is just, so now what your prediction value will be, just max vote of all the data points. Max vote of all data points. Data points. So this is the highest bias model, right? So highest bias model. So bias is too much. Are you convinced that the bias is too much in this? Because now you have oversimplified your model, because now your prediction is only mean or mod or some statistical value or some max vote of all the data points that you have, right? You don't even have to calculate distances now. You have made it so simple that you're just computing max vote of all the data points. Correct? So what is the answer then? If we are convinced that the variance has decreased and bias is too much. So bias increases and variance decreases. Okay, so B is the answer. Okay, so B is the correct answer, but let me go over it because this is a little paradoxical and I can understand why you guys are not able to get your head around it. So in K-nearest neighbor, bias variance trade-off is kind of paradoxical because it might seem that having just one neighbor is the simplest model and it's more accurate to measure. It's usually more accurate to measure the complexity based on the model variability. How much is the model varying your prediction values, right? So in this context, if you have large values of K, you will have lower model complexity because your variance decreases, because your um, variability in the prediction values has now decreased. It's not overfitting anymore, right? So your variance definitely decreased, right? And why does the bias increase? Bias increased because now you have oversimplified your model. Now it's a very simple model. When K is equals to N, then you're just computing the max vote of all your data points. And when it's say a regressor, you are just computing mean of all the points or mode of all the points or median of all the points, right? So it's an oversimplification of the model. So when K is equals to N, model is oversimplified. Fine. So little paradoxical, hence you should think about it again. Like whatever we said over here, did it make sense? Okay, so usually people don't get it in one go, but go over it again, you will understand. Okay, so let me show you these plots again. Okay, and Rohan, this will answer your question why I said that decision boundaries are like segments. Okay, so this is bias. This is K. So this is a this is a K-nearest neighbor that I've taken from this particular YouTube video. So you can check that out. So here they have plotted the decision boundary for K is equals to 1, right? So you can see that it's overfitting on every data point, right? It's fitting every data point into the boundary, right? Here, when K is equals to 3, can you still see that there are line segments over here? So when you actually plot the decision boundary, it will be line segments, right? You can see that now this is less variable, like it's varying less, right? Over here also, this decision boundary is like much smoother when you have K is equals to 10. Fine. So this is how your decision boundaries changes when you go from K is equals to 1 to a higher number of K. Fine. I'll take some doubts. If we have option only to reduce one of bias and variance, then which one should we go off? I don't understand the question. So if you have if they're asking that what happens if increasing bias is increasing or decreasing, variance is increasing or decreasing, it should be a multi-select because both of this happens. So bias is also decreasing and bias is also increasing and variance is decreasing. Okay, I think that was your question. If not, please let me know what exactly is the question. I am little doubtful.
Yes, ma'am. Ma'am, the ideal scenario is to have both values of bias and variance both as low.
Low,
But
yes.
if we are having but if we are having option to decrease only one of them,
Hmm.
so which one should we go for? Is having higher variance more tolerable than having higher bias or vice versa?
It depends on your use case. Basically,
Okay.
I'm not able to come up with the example right now, but usually it will depend on your. So suppose you will build some model, right? And there'll be some evaluation metric associated with it.
Hmm.
Correct, based on your use case. So that's something that you should rely on to take this decision. But having a high variance model means that you have overfitting and it's definitely not going to do well in your test it, our production setup, wherever you are getting unseen data, right? So oversimplification might sometimes works, but if you can definitely see that there is overfitting, you should try to reduce variance. But obviously, again, it depends from your use case to use case. Mostly, I would try to decrease overfitting because I will definitely know that will not perform well in the production. But
Okay.
scenario to scenario, it can change also.
Okay.
Okay. Okay. Okay. Fine. So here we have the decision boundary. Okay. Cool. So let me move over to this answer. So the answer is B, as you guys already told me. This is the correct answer because with K is equals to N, model is oversimplified. Fine. So this is a very simplified model. And also the bias is high and variance is equals to very low, approximately equal to 0, or it will be 0 because same predictions you will get for every data point, right? Fine. Okay, now comes the difficult question. And this is the last question for this particular lecture. So let me go over this. So you have, we have two labels, okay? So you have two classes. One is class 0 and one is class 1. We are given a test point X. You are given a query point and its K-nearest neighbors are Z1 to Zk, where Zi is the closest neighbor. Okay, so Z1 is the closest neighbor, Z2 is the second closest neighbor, Z3 is the third closest neighbor, and so on. Suppose that the probability that the label of Zi is not equal to that actual label of X. Okay, so we are saying that some test point X we have, and whatever its true label is, the probability that the label of the ith nearest point is not same is P. Right? Also, we'll have to assume that all the distances are unique. So there are so the ith closest neighbor of X is unique for all I. It means that there is no data points which are at equal distances from the data point X. Okay, so it's not like, so there is no ij such that the distance between Z and distance between Z and X and Z Zi and X and Zj and X are equal. Okay, so the distance, maybe I should write it like this. So distance between X and Zi is not equal to distance between X and Zj for all I not equal to J. Okay, so no two neighbors are at the same distance from the query point X. Okay, for this question, we'll assume that the probability that the label of the ith data point, ith training point is not equal to the X class is 0.2. Now you have to tell me what is the probability that 3 nearest neighbor classifier makes a mistake on X. Can we do this? Okay, so this is one of the questions that I had given in AIoT, All India Open Test last year. And this was the most incorrect answer. And I think this was the most difficult question of K-nearest neighbors that you can have. Okay, so let's solve this. This is very simple, actually, if you think about it. Okay, so first, let's see that when will be the prediction of X be incorrect. So prediction of X will be incorrect. Prediction of X will be incorrect if exactly two neighbors make incorrect prediction. Right? Plus exactly three neighbors. Three neighbors make incorrect prediction. or have incorrect, sorry, have, let me correct this, incorrect label, or say the label which is not equal to excess label, right? Plus exactly 3 neighbors have incorrect label. Correct? Can we do this now? So how will you do this? So probability that, so we have to calculate the probability. Exactly 2 neighbors are wrong. Different plus probability. Exactly 3 neighbors are different. Now this is very simple. If you look at this like this is very simple. You must have seen this in your probability questions. And again, probability creeping in your machine learning. Fine. So let's do this. So what is the probability exactly 2 neighbors are incorrect? So there will be 3C2, right? And so 2 neighbors are incorrect. So this is the incorrect, as in the label is not same as X's label. So there are 2 neighbors which don't have the correct prediction, and there'll be just one label or one neighbor which has the correct prediction, right? And exactly 3. So this will be 3C3. So all of them have the incorrect prediction or the different label, right? So we were given that P is equals to 0.2. The probability that the label Zi is not equal to that label of X, correct? So now we'll solve this. 3C2 is 3. This is 0.2 power 2, 0.8 plus 3C3 is 1, right? And this is 0.2 to power 3. So this is 0.2 to power 2. I'll take common. This is 3 into this. This is 2.4 plus 0.2. This is 0.04 into 2.6. Correct? Now I'll take 464, carry over 42810. I'll take 3 points, right? So my answer is 0.104. Fine. So this was the question that was the most difficult for the last All India Open Test that we conducted. But this is really just simple. You should understand how the K-Nearest Neighbour classifier works. And if you know that, you will be able to solve this very easily. Fine. So that's all I had for today, I guess. Yes. So we talked about K-Nearest Neighbour classifier. We talked about the decision boundary of the K-Nearest classifier. And then we looked at the bias-variance paradox also, and we solved a lot of questions, right? So the question that is remaining is, how do you choose the K? Right? Because nobody asked me, like, how do you choose the K? This is something that we'll cover in the next class. This is where your cross-validation will come in. Fine? So that is mostly it for the K-Nearest classifier. K-Nearest Neighbour classifier. There's not much into this. I have attached 3 videos in the lectures. In those 3 videos, I had solved a lot of questions last year on K-Nearest classifier, K-Nearest Neighbour classifier. So please go through them. Some of the questions I've already included in this lecture. Some of them you will find new. So I'll suggest you quickly go over those 3 videos that I've embedded in the lectures after this particular video. Fine. So in the next class, we'll begin with how to choose this K, and we'll take up cross-validation. Okay. So any doubts?